Okay, so I would like to thank everyone joining today, either in person or remotely, this new event from the Stage International Speaker Seminar Series. You are welcome to ask questions during the talk or after the talk or through the chat box. I'm Laurent Briolet from the Lonnenfeld Tannenbaum Research Institute and one of the Stage mentors. I'll start with a few acknowledgements. So first, I wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. Also, Stage operates with the support of CanSci Ontario, an extra departmental unit in the Faculty of Arts and Science of the University of Toronto. The International Speaker Seminar Series are sponsored by the Hospital of Sick Children, the Lonnenfeld Tannenbaum Research Institute, the McLaughlin Center, UHN, and the U of T Department of Statistical Sciences. So today we are happy to have Dr. Li Shu as the guest speaker. Dr. Shu is currently a professor in the biostatistics program at the Fred Hutchinson Cancer Center and an affiliate professor of biostatistics at the University of Washington. She's been actually at the Fred Hutchinson Center since her graduate studies. Her work involves both statistical method development, especially in the area of survival data analysis, as well as collaborative research in observational studies of cancer and other chronic diseases, with a focus on the analysis of genetic, molecular epidemiological data and survival outcomes. Specific areas of interest include absolute risk estimation and risk prediction, genome-wide association studies, genome interaction studies, and the integration of diverse data sets. Additionally, she's interested in evaluating the performance of risk prediction models and the cost effectiveness of screening strategies in large-scale cohorts and real-world settings. I personally have followed your work with great interest related to frailty models, applies to family studies and to other designs, including applications to the BRCA1 and 2 families. Dr. Shu is the lead biostatistician of the Genetics and Epidemiology of Colorectal Cancer Consortium, GECO, the largest consortium for colorectal cancer, where she directs the efforts in developing and evaluating genome-wide risk prediction models for colorectal cancer in diverse populations. Dr. Shu holds the Ross Prentice Professorship at the University of Washington and is an elected fellow of the American Statistical Association. She has authored more than 250 papers. So today, Dr. Shu will talk about advancing cancer risk prediction across diverse populations, polygenic risk scores, and beyond. So please welcome Dr. Shu.
Thank you, Lauren, for such a nice introduction. I have a really nice visit so far and a nice dinner, great dinner companions, met a few faculty and students yesterday and this morning. And I also got a special treat that I went to visit a gallery with Esther and get to see a few Canadian paintings and women painters. So it was really a great visit. So today, the title of my topic is Advancing Cancer Risk Prediction Across Diverse Populations, Polygenic Risk Scores, and Beyond. So I'm going to actually cover two topics. The first topic is our efforts in the last 6-7 years in developing risk prediction models for colorectal cancer based on the genetic, lifestyle, and environmental risk factors. So this topic is completely applied project. There's no methodological development for this topic, but I really enjoyed this research work and sort of, so a little bit part of my journey here is that when I started my research at Fred Hutchinson Cancer Center, and my research is mostly focused on the cancer etiology, so like more on the discovery side. And so this work is, I feel like a long time that comes that sort of translating my etiological works into the clinical care. So I never thought that my research ever end into this stage that I get into a little bit more the practical aspect of it. The second topic is a little bit more statistical methods work that we have done recently is to recalibrate a risk prediction model to another cohort. So often, as you have seen many papers and there are many risk prediction models that have been developed. And the question is that, can we use the risk prediction model to our own cohort, or can we sort of recalibrate for other target populations? So let me just jump into the first topic, and please stop me at any time if you have any questions, because I do like interactive discussions. So a little background about colorectal cancer. So colorectal cancer is actually third most common cancer in the United States and the second leading cancer cause just after lung cancer. But the colorectal cancer is actually very preventable because there are effective screening tools that are available. For example, colonoscopy and the FATE screening, which is like stewed or blood-based tests. However, so actually the U.S. Preventive Task Force recommends average risk people to start screening at age 50, and the age has been recently lowered to 45 years old. So despite that, the effectiveness of the screening strategies, actually about 1/3 of eligible people actually do not receive colorectal cancer screening. So there are factors in terms of making the screening decisions. Often there are really just two factors. One is a family history or familial syndrome. Often individuals who have a positive family history, they will be recommended to start screening at age 40. Now, of course, it's lowered from 50 to 45, recognizing there is an increasing trend in colorectal cancer in the young people. So by reducing the screening age from 50 to 45 in US, it has been estimated there are additional 22 million individuals that will be eligible for screening. So obviously, this will add a lot of burden to the healthcare system. So it makes it more pertinent to identify individuals who are at elevated risk for developing colorectal cancer who could potentially benefit from earlier screening. So so before I jump into the data and the results, so I've been involved in a consortium called the Genetics and Epidemiology of Colorectal Cancer Consortium. This consortium has been led by Ricky Peters, a genetic epidemiologist at the Fred Hutchinson Cancer Center. So the consortium started more than 10 years ago. So it is a growing resource. We started with only 2 or 3 studies of GWAS data, but now it has more than 80 studies and have over 150,000 participants in the study. Roughly speaking, half of this 150,000 participants are colorectal cancer cases, and the other half are controls. One of the foci of the consortium is actually to look at the gene-environment interactions. And we expand this cohort also to the tumor data. So we have sequencing data on the tumors so that we can actually understand a little better about the molecular epidemiology, essentially to examine or investigate how the risk factors associated with certain subtypes of tumors, and also survival analysis based on the tumor markers, as well as the germline genetics and lifestyle environmental risk factors. But today, I'm only talking about the risk prediction model for predicting cancer risk. So it has been well established that both genetic and lifestyle environmental factors that contribute to colorectal cancer. So this is based on the Scandinavian twin registry study. So what they have done is essentially just compare the monozygous and the dizygous twins and to estimate the contributions from heritable factors and the environmental factors. So highlighted here is colorectal cancer. So roughly speaking, about 1/3 of colorectal cancer risk is attributed to the heritable factors, and 2/3 is actually from lifestyle environmental factors. So based on this information, we developed a risk prediction model using some common risk factors that have been established or investigated for colorectal cancer. And this include height, body mass index, education, type 2 diabetes, smoking, alcohol, aspirin, NSAIDs use, hormone replacement therapy, dietary factors, and physical activities. So we look at all of those risk factors and we call it the E-score. So essentially a sum of those risk factors. We also look at the construct a G-score based on the 33 SNPs that were discovered at that time to be associated with colorectal cancer risk. And then we categorize the E-score and G-score into quartiles. As we can see here that both E-score or E factors and G factors contribute independently to colorectal cancer risk. And the effect size are roughly the same. It's about increased risk by 1/3 per quartile increase. And family history, as we all know, increases the risk for colorectal cancer. The endoscopy history here is a colonoscopy history based on the information we have is highly protective. It reduces the risk by 50 to 70%. So when we developed the risk prediction model, then we thought what we could use this model for. One idea that we have is that can we use the model to recommend people when to start screening? We adopt a strategy of equal risk, equal management, meaning that if an individual reached risk, let's say 1% at the age 55, then the individual will be recommended having screening at the age 55. Or based on the risk prediction model, if the person reached the risk, 10-year risk at the age 45, then the individual will be recommended to have screening at the age 45. So what we draw here is essentially on the y-axis is the recommended starting age for screening, and x-axis is the risk score in percentile. On the left-hand side is for individuals with positive family history. On the right-hand side is those with no positive family history. And the color coding, one is for women, the red color is for women and blue color is for men. So women actually have a lower risk for developing colorectal cancer than men. So you can see that the recommended age for screening for women tend to be at the later age compared to men. And individuals with a positive family history would be recommended to have screening age earlier compared to those without family history. But what I want to draw your attention is that we do see this decreasing curve along this risk score. So the higher the risk score, the earlier the individual will be recommended for screening. So below the figure are just the quantile. So for example, at the 1%, for men, you'll be recommended to have screening at the 55. But if the risk score is at 99%, then the same person, the individual, a man would be recommended to have screening at age 38. So there is a wide range of age for starting the screening. So we're sort of encouraged by this results. But since we have we have accumulated a lot of GWAS data, and having a G-score based on 63 variants seems unsatisfying. So we, basically in the last I would say 5, 6 years, we spent almost all our efforts on improving the risk prediction based on the genetic factors. So we started off with non-Hispanic white study participants. So we have about 55,000 cases and 65,000 controls. We set aside an independent study, roughly 2,300 cases and 140,000 controls. And this validation study was not used anywhere in the world, including anywhere in the world for the GWAS discovery. So we can honestly say that this is an independent validation for the polygenic risk score that we have developed. So we considered a number of approaches, but broadly speaking, those approaches are grouped into 3 categories. One is based on known variants. So at that time, we have 140 variants. And then the second approach called selection plus machine learning. So dealing with GWAS data, so not only we have this large number of predictors, but we also have a large number of samples. So the dimension is high, not only in the predictors, in the P, but also in the N. So dealing with this like large or ultra high dimensional data using machine learning algorithm, it just has been very challenging. So what we have done is that we sort of did a selection. We divided data. We use part of data to select the variants that are based on marginal association statistics, and then use this subset of the variants and running more complicated machine learning algorithms such as XGBoost and support vector machine, so on and so forth. So the number of variants that went into the machine learning algorithm is about 10,000 variants. And the last approach, actually, we truly used the genome-wide variants. We didn't do any pre-selection. And that involves 1.2 million variants. And as I just sort of argued with, trying to sort of tell you that running those machine learning algorithm with the ultra high dimensional individual level data is very difficult. But I think the recent developments that developing this polygenic risk score based on the summary statistics that have made it possible to use this entirety of this 1.2 million variants possible. So as we can see here that every time we include variants, our AUC estimate has improved. So based on this 1.2 million variants, the AUC estimate is 0.64. So a little bit, I just want to digress about this summary statistics based the methods. So actually I'm very interested in this area, but I have some work in some other topics, not in the risk prediction. But the argument is this. So think about a linear regression model. So when you fit a linear regression model, y equal to x transpose beta. So x is p dimension variance. So there is a explicit form, which is x transpose x inverse and x transpose y. So if we look at this into 2 components, x transpose x is just covariance of x, and x transpose y are the marginal correlational covariance between x and y. So x transpose y is truly what you need is a large sample size because effects of genetic variants are very modest. We need a very large sample size to get this x transpose y correctly. However, to estimate x transpose x, the covariance, we don't need 150,000 individuals. We have 5,000 individuals, we can get a relatively good covariance matrix. So by dividing this into 2 parts, we can actually develop a lot of summary statistics-based methodology that make use of the summary statistics based on marginal association, and then having the x transpose x either from a reference database or your own individual level genetic data, and to do this multivariate analysis. So we have compared, so this is based on the different topics. So we look at, so this is essentially TWAS analysis to look at predicted gene expression association with the corrected cancer risk. And also we look at the pleiotropy effects. So essentially the figure on the left-hand side is the the p-values associated for the particular gene expression, and p-value on the right-hand side is a pleiotropic effect of a genetic variance. So on the x-axis is the individual level data-based p-values. On the y-axis is the summary statistic-based p-values. Since I do have individual level data, even though I don't like to, to analyze my individual level data all the time, but I have the data so I can just check it out. And this is based on the binary outcome. As you can see that there's a very nice correlation between individual level data based p-values versus summary statistic based p-values. So I just digress a little bit just to talk about the development for the summary statistics based methods. So of course then we will not stop there. So we want to expand our PRS development to include other racial and ethnic groups. So through our partner consortia, Asian consortia, we were able to access to the summary statistics. Now we don't even need to access to individual level data. The summary statistics for Asian population based on 22,000 cases and 47,000 controls. The sample size for non-Hispanic white also has increased, but not in a dramatic fashion. But at this point, we wanted to also see how the model performs in all racial and ethnic groups. So we included Asian, Black African American, Hispanic, as well as non-Hispanic white populations. So those are the sample size that I'm listed here. So what we have seen here, so we have, again, look at the various approaches. We look at the Eurocentric, essentially the PRS we developed earlier. And we also look at the approach ancestry specific. So those approaches essentially to develop the PRS for a particular ancestry while leveraging the information from other ancestries. And the last column, I call Asia and Euro or trans ancestry. We simply just like do a meta-analysis of Asian and non-Hispanic populations, and then treat them as just one summary statistic and develop the polygenic race score. So what we have seen here is that the most significant improvements are in Asian and the Hispanic populations. So the message to me is kind of clear that it's so important to include the samples of the populations that you want to apply to. Okay, so we also see a little improvement in non-Hispanic white, but the most improvement that we have seen is in Asian and Hispanic. So the ancestral groups for Hispanics are mostly coming from non-Hispanic white as well as Native Americans. But the performance of the PRS in Black and African American population remains behind. So another point I want to make is that we see that this combining this Asian and non-Hispanic white, just do a simple meta-analysis and develop the polygenic race score, appears to perform the best and has the smallest confidence interval. So I think it kind of makes sense. I think I mentioned to this point to a few people before. What research has been shown that most of the causal variants actually are transportable between populations, but the genetic architectures are different across populations. So for white population, it's well known that the LD block is longer than, for example, in African American population. Since we include 1.2 million variants, obviously this 1.2 million variants are not necessarily causal variants. In fact, the vast majority are probably just markers. They tag the causal variants. So if we use the tags from the non-Hispanic white population, it may not be good tags in African population. But by combining the data from Asian, non-Hispanic white, hopefully African American Black population later on, we can better pinpoint the causal variants. So that's probably why we see the improvement here. So AUC is only just a metric. So we also look at relative risk of PRS compared to the mean of the individuals for each group. This basically tells a similar story as what I've shown in the AUC. The relative risk per standard deviation is similar for Asian, Hispanic, and non-Hispanic white, essentially increase the risk by 64%. But for Black and African American group, it's only 40%. So we're currently developing a web tool for colorectal cancer risk prediction model. There are many people who probably have done the genotyping or have submitted their DNAs, blood samples to the swab to 23andMe or any other companies, and to get their ancestry information or sometimes maybe some phenotype information. So we will use those genotyping data from 23andMe if an individual is interested in knowing their colorectal cancer risk, and doing these various steps, format checking, convert the file, and then phasing and doing imputation, and provide the polygenic risk score calculation, and then ultimately the absolute risk estimate. So this whole process currently takes about 5 minutes. During this 5 minutes calculation, we also send out a questionnaire. We ask the individual their education, their racial ethnic background, and all those lifestyle environmental risk factors. So hopefully by the time they finish their questionnaire, then we are done with our PRS calculation, and then we can provide an overall absolute risk estimate back to the user. So this is currently sort of in the testing phase, and we hope that in the next few months we will be able to try it out in the public. Yes, please.
So when you return the result back to the participants, do you give it to them quantitatively or qualitatively?
Super good question. At this point, sure. So the question is that we return the genetic results. Do you return the results quantitatively or qualitatively? So current thinking is that we're going to return the results qualitatively. Obviously, you can give any numbers and any risk, particular points. We did actually a pilot study before. If we give them the estimate, especially if the individual look at their score and seems below, let's say me, they'll say, oh, maybe I should not do screening, which probably I don't know whether they should or should not, but certainly not. The healthcare organization is not going to like it because they want everybody doing the screening, follow the screening guidelines. So what we're going to do is probably just going to give average risk and elevated risk. So any other questions? Okay. Yeah, so I just want to, again, emphasizing that when we incorporate the Asian genetic data, we see that improve the performance for the Asian and Hispanic population, but there's still a long way to go for African American population. But so far, the GWAS sample size for African American or Black population is very limited. We have approximately 2,000 cases and 20,000 controls in our consortia. So obviously, compared to 20,000 cases for Asian, 80,000 for non-Hispanic white, this is just a small fraction. We're looking for collaborations, and if people have data on Black or African American population, we'll be delighted to collaborate. Part of the issue is that there are a lot of cohorts that are very inclusive, but colorectal cancer is still relative infrequent disease. So even though we have access to African American population from, let's say, a biobank data, so the N is still relatively large, but the number of cases is still very small, but we need the cases. So the sample size, unfortunately, is still very limited. So then we have to think alternative strategies. So one of the strategy we were thinking is to incorporate the functional variants. So the idea is that if the variants are functional, based on whatever criterion, then they're likely to be causal. So focusing on those likely causal variants, hopefully the polygenic risk score are more transportable across different racial and ethnic groups. So our initial exploration seems to suggest this is not a bad strategy, but again, the improvement is still relatively limited. It's still not up to the bar of non-Hispanic white. But this work is still ongoing. We're trying to incorporate as many functional annotations, scores into our risk prediction modeling. And the last point I want to make is that even though we are making progress in improving the prediction based on the genetic variants, I think our progress for predicting risk based on lifestyle and environmental risk factors remain to be limited. We actually applied our model based on the E-score to an EHR-based research cohort. And even though the AUC based on our research cohort is not bad, but as soon as we apply our model based on the E-score to the EHR-based data, the prediction basically falls flat. I think it just says that it has been just very difficult to collect the lifestyle variables accurately. There's a lot of measurement error, lots of biases that go into the data collection or reporting. Yeah, I think this is ends my first half of the talk. I'll pause for a second and pause for a minute and to see whether there are any questions. Yes, please.
Very interesting. But I don't understand. You have a cohort, would you call it, as well? You take the healthy women in the study, and follow them forward to see if they develop colon cancer, they did not. You just did in the case of the 26.
So the question is that, do I have a cohort that follow those patients to see whether they will develop colorectal cancer, or do I just have the case control studies? Both. So for the training data set, we just putting all the studies that we put together, and those include population-based case control studies that could be conducted as as far back as 30 years ago, or nested case control studies. That's even though they're cohort, but that's really within the cohort studies. But the validation data set, especially for the non-Hispanic white, is actually based on a cohort study from Kaiser Permanente in Northern California.
Well, I'm just suggesting you do a little more testing in this cohort. You look at risk factors rather than screening. So you have the idea that you can identify a risk of the person, then you say, we're going to go not. There's many predictive factors that are risk factors that are much more powerful than this. For example, the CBC and the platelets. We've done many studies showing the platelets over 400, the risk of colon cancer goes up 6 times. We've done studies which shows that I can take your CBC, look at the hemoglobin, follow that, and predict the high level of accuracy whether you're going to get colon cancer the next year. And then now everybody's running around doing liquid biopsies, ctDNA, episomes, et cetera. To me, I mean, a full program, a clinical program that I would endorse would include both the lifestyle factors, the SNPs, and an annual reevaluation of a CBC or whatever, because you guys are focusing on risk factors. You're not focusing on screening factors other than you say go them right from the risk to the colonoscopy. There's 10 things you can do in between to better refine the risk. They're not risk factors, that they're biological factors that indicate the early presence of stage 1 colon cancer.
I'm less familiar in the area. I would love to hear more about it, maybe after the talk. So indeed, we're more focusing on prevention. So what we see here, at least our thinking is that to use this to stratify people into, let's say, high risk. And at this point, we're not even thinking very far. It's just to see when this person should have screening.
You can't call it screening prevention. Prevention is that the sensitivity.
So, sorry, can you say the questions again? Yeah.
When you talk about, what do you mean by prevention? Colonoscopy to remove benign adenomas or giving them aspirin?
Yeah, sorry, the colonoscopy removing the adenomas. So, yeah, so colonoscopy. So actually, really what we're interested to predict is the advanced neoplasia. So that includes colorectal cancer and advanced adenoma. That's really what we're interested in, but most of our data is on colorectal cancer. We did look at the prediction of our polygenic risk score in association with the advanced neoplasia, and the prediction is still a little less, but remain to be strong. So as you would have imagined, the polygenic risk score, actually the prediction of the polygenic risk score for polyps, adenoma, advanced adenoma, and colorectal cancer is increasingly stronger.
Instead of like using like a genetic variance alone, is there any way that you can like use the gene expression data to make a better prediction of the risk? For example, like if you have a like gene expression from a like tumor tissue, and probably it'll help like prediction. At the same time, if you already like collecting gene expression from the tumors, it's probably like cheating in some sense.
Yeah. So this is to predict people to have cancer in the future, or develop cancer in the future. So it's not entirely clear to me how to make use of the information of gene expression in tumor data. Presumably that could be used for example, to identify tumor subtypes and to maybe instead of looking at the association of the genetic variants with colorectal cancer as a whole, but more looking at the association with genetic variants, for example, with a particular subtype. Like in colorectal cancer, there is a MSI high, MSI low or stable. Then we can sort of make the prediction more refined. So we did actually try approach to use a genetic variants to predict the gene expression in the blood. That didn't really improve our prediction.
Thank you.
Yeah.
I'm wondering, like, have you divided your models calibration in some like intersectional groups? Like, is that possible at a given risk score? Like a black male is sicker than, or like a higher risk than a white female, something like that.
So your question is that whether we have looked at in the subgroups.
Yeah, like some like not just ethnicity, but like ethnicity and age or ethnicity, sex, something like that.
Yeah, so we did. So there are more results in our paper. We also look at by age, especially recently because there's an increasing trend of colorectal cancer incidence in the last decade. So there is a lot of interest in the early onset. So we note that actually polygenic risk score has a stronger effect for earlier onset of colorectal cancer. Whether we did more refined categories like male, black, I think we did that too, actually. And we also stratified by family history and sex and so on. So, yeah.
Yeah, about one question. I'm not sure how you use this framework to determine what could be an optimal age at colonoscopy screening, because it seems a complicated question. Like,
it is a very complicated question. So the figure that we showed is more just to see like. So the strategy that we use there is equal risk, equal management. So meaning that if you have the same risk, and then this should have the same recommendation. That's essentially sort of the principle that we followed. But this one, of course, has a flaw because age is the strongest risk factor for cancer. So, you know, an 80-year-old will likely to have a much higher risk, regardless what the risk factor is, has a higher risk for developing colorectal cancer than a 50-year-old. But would you sort of recommend 80-year-old to have colorectal cancer screening, colonoscopy, going through the colonoscopy? It may not be a simple answer, right? It also depends on his other risk factors, his comorbidity situations. So I think it's not a simple answer. So recently I've heard an argument. So instead of this equal risk, equal management, maybe what we should have considered is the life year scaled. Then you will put more weight on those younger individuals because they were more likely to benefit from the reducing the risk for colorectal cancer. But it is a very good question. It's very nuanced. So maybe I'll just move on to the next topic. So this is a work that I have done in the last 2 or 3 years. This is to essentially, if we have a model like a colorectal cancer risk prediction model we have developed, but if we want to apply this model to another target population, for example, Kaiser Permanente population, how are we sure that this model is applicable for the Kaiser Permanente participants? And I think this recalibration or calibration is a very important topic, because if you tell somebody saying you have 10% risk for developing colorectal cancer, but actually in another population, maybe it's only 8% or 5%. So you sort of overestimate the individual's risk for developing the cancer. So at least not necessarily we know individually, because of course individually there's always an individual uncertainty there, but on average, if we tell somebody had 10% risk, they should, you know, if you look at a large number of individuals, on average, they should have 10% to develop colorectal cancer risk. So this is a sort of the topic for my second half. Now, when we talk about the risk, earlier, I often sort of focus on beta, so essentially the association. But now when we talk about the risk, it actually involves another element, which is a baseline hazard function. So for simplicity, if we consider a Cox proportional hazard model, so the probability of developing disease by time t is 1 minus e to the lambda 0 of t. The lambda 0 of t is a cumulative baseline hazard function times e to the beta transpose z. So what I show here is the baseline hazard functions from 3 cohorts. Women's Health Initiative, the solid line. And on the left-hand side is the Women's Health Initiative. And the 2 lines below the solid lines are the PLCO trial, the prostate, lung, colorectal cancer, ovarian cancer screening trial. The 1 line is corresponding to the control arm. The other line is corresponding to the intervention arm. On the right-hand side is UK Biobank, but we sort of divided it into 3 regions, England, Scotland, and Wales. In both cases, we can see that the baseline hazard functions are different. So if we use WHI data, the Women's Health Initiative data, to estimate the lambda 0 of t, and blindly apply this model to either PLCO cohort or UK Biobank cohort, we will overestimate the risk for those individuals. So what can you do about this? The easiest is to re-estimate risk prediction model using the data from the target cohort. Yes, for PLCO or UK Biobank, there are plenty of cases, we can redo that. But often when you apply the risk prediction model to a new cohort, we don't have cases, especially if we want to apply the model to re-stratify and follow them until they have cancer or some other outcomes. We definitely do not have the data to re-estimate the risk prediction model. Especially for colorectal cancer, the incidence rate is, as I mentioned earlier, is infrequent. it will require a large cohort in order to estimate this parameter reliably. On the other hand, there are a lot of external information or summary information that are available from the target cohort. For example, overall disease incidence rate, or some patient characteristics. What is on average the BMI or mean or variance of BMI, or some other information. So the idea is that can we use those summary information to recalibrate the baseline hazard function that would be consistent to the target cohort? Again, the approach that we consider is fairly straightforward. If we know the disease or overall survival probabilities from the target cohort, let's say 5-year survival probability, or the age-specific disease incidence, we can simply just constrain our survival probability by the known quantity. So S of t is, let's say, overall survival probability from the target. Then we can just constrain this e to the minus lambda 0 of t, e to the beta z equal to S of t. Now, if we assume the covariate distribution is the same between the source and the target cohort, on the left-hand side, the expectation can be just replaced by empirical averages of your own source data. And we can estimate the lambda 0 of t essentially by solving this equation. But it's a big assumption that to have the same covariate distribution between source and target population. So to relax this assumption, we thought maybe we will also use the known summary statistical information from the target cohort. So by essentially make use of this log empirical likelihood to essentially in a simple term or in an intuitive term is to reassign the mass of each individual in your source data so that the mean or variance, whatever the summary statistic you have from the target will be same as the target cohort. Now, once we get this omega I or Wi, and we can plug into the equation that I showed you in the previous slide, and again, to obtain this lambda 0 of t by solving this simple equation. Right? So this is the empirical likelihood, and this is the constraint. And mu1 is supposed to be mean of the BMI from the target. So we proved some theorem. So if indeed actually the covariate distribution is the same, and we showed that this weighted baseline hazard function estimator is consistent to the true baseline hazard function. If the summary statistics is from a very large sample size, you can actually gain the efficiency from incorporating those external information. So if the covariate distribution is different, it still has a nice statistical property in terms of asymptotic normality, but it converges to something else. So theoretically, we do not have a consistent estimator. But it's a well-behaved estimator, but it's not a consistent estimator. So then the next question is how biased is the estimate? So we sort of look at essentially how close this empirical likelihood of update distribution to the target distribution compared to the source. So if we make some improvements, sure, it's not necessarily the best, but at least we're one step closer to the truth. So what we again prove here that if you have some information from the target, you will for sure improve compared to your source distribution. And if you have more information, and you will improve even more. That's essentially what this theorem says. But that's kind of dry. So when we say, okay, let's look at how good or how bad the bias is. So we consider two binary variables. And the joint probabilities, the Pij and Qij, are from source and the target. And we just take the values from 0.05 all the way until 0.85. We just take the value for source and target. So in total, the combination is close to 1 million combinations. So we look at each combination and we just say, how good is this empirical likelihood-based updated distribution performs compared to the source distribution. So the left-hand side is this KL, the distribution of the KL distance, essentially to compare the two distributions between the target and the source population. And the second one, the green one, is between the target and marginal correlation, just using one margin. And third one is using two margins. So rigorously speaking, even though we have updated our distribution using two margins, but this is not, this does not quantify the joint distribution because we only look at the marginal probabilities. But even in this situation, we can see that the the KL distance becomes smaller and smaller each time we add more summary statistic information. So on the right-hand side, we look at the difference of the KL distance between the source and the target, as well as our updated ones. So again, the message is the same, that we see the improvement each time we add more summary statistics. But the interesting point that I want to make here is that, as I mentioned here, that having two marginal does not necessarily mean better with one marginals, because this is not it does not capture the joint distribution of the two variables. So in this case, we actually do see occasionally that the KL distance for imposing two marginal summary statistics is worse than imposing one summary statistics. So what are those situations? Those situations are if the joint probabilities in the source is, let's say, nearly independent, less than 0.2, but in the target is 0.8, is highly dependent. And that's where we see things start to break down. So only in the extreme situations, then we see things break down. So the bottom line is that theoretically it is biased, but in practice, it actually works quite well. Similar message for continuous variables, but in the interest of time, I'll just move on. So we applied our methods to couple data, three cohorts. So we use the WHI data as a source cohort, and we recalibrate to PLCO and as well as UK Biobank. So here I just want to show that there are differences in the prevalences of some risk factors. For example, for the PLCO, as by design for the intervention arm, there are far more individuals have screening, but fewer individuals in the control arm have screening. And for the UK Biobank data, we see that actually there are fewer individuals having screening compared to women's health initiatives. So we also see there are some differences in other risk factors, for example, exercise, NCUs, and estrogen status. So I probably just skip that one. Again, just because of the time. So then we look at the calibration. So the left column is using the WHI model. If we don't do any recalibration, and we want to see how that performs in each of those target cohorts. The first two are the PLCO cohorts, and the bottom three are the UK Biobank cohorts. And we can see that, as we have already guessed it, that we would, because the baseline hazard function is much higher in WHI, we would overestimate the risk of developing colorectal cancer for those individuals in the PLCO cohort, as well as in the UK Biobank data. And the last column is based on our weighted empirical likelihood methods. And we can see that our recalibration is more or less on the 45-degree line. It's not perfect, but it's much better than the WHI data. I also want to mention this work which just accepted by Lifetime Data Analysis. So we extended this idea to population-based case control study design. So the nice thing about population-based case control design is that it's very efficient because you collect cases and retrospectively. And it also has some nice properties. It has been established more than 40 years ago. Sometimes I'm losing the time. That in the sense that if cases and controls are matched on the time, the odds ratio actually approximates the hazard ratio in the Cox model. But because of the oversampling of the cases, the baseline hazard function is not identifiable, right? So it's understandable. So there's this brilliant work by Mitch Gill in 1989. So he derived that there is a relationship between the baseline hazard function, baseline hazard rate function, with this lambda of t, which is a composite hazard function, through this quantity called the attributable risk quantity. So what this one is, essentially is the expectation of e to the minus beta transpose z, and with respect to the distribution for those cases at time t. So what that means is that this quantity actually can be estimated using your case data only, because you have beta, you have this distribution, and you have everything. So all you need is a lambda of t. But in epi study, actually, most of the epi studies that I've dealt with, this conditional probability is roughly constant, actually. So you can approximate this distribution just simply based on the case, instead of looking at time t. We also have a method to estimate this non-parametrically using smoothing kernel smoothers. But actually, in practice, just assume their time invariant is good enough. So again, just like the cohort data that I showed to you, we can estimate this expectation by the empirical average of the covariate distribution among cases. Just like the work that I've shown to you earlier, we can recalibrate by using the empirical likelihood, making use of the information or summary statistics that from the target cohort. Okay, so quick summary. The summary statistics are everywhere, ubiquitous, and are far more accessible than individual level data. In my case, even though I have individual level data, and I don't want to deal with individual level data, I would not want to deal with this 150,000 individual level data. It's too cumbersome, it's prone to mistake, it's just not a good idea to deal with it every single time. But it's very useful for me when I develop methods. I can always go back to validate, to say, should I have individual level data? How does that perform? The other point I want to make is that leveraging the known information can help to recalibrate your model and improve the efficiency in some cases. So I think I guess this is sort of in the broader context. There's a lot of work in this data integration, transfer learning. They're all it's all in that kind of space. So finally, I want to acknowledge the Minta Thomas, who has been leading the polygenic risk score development, Jiaying Zheng, who has been leading this recalibration of risk prediction model work. And there are many students and postdocs and colleagues. I probably will not list the names here. Really, really lastly, I want to mention that the collaboration with the GECKO Genetic and Epidemiology Colorectal Cancer Consortium has been extremely productive and fruitful. It gives me the motivation for my methods work, and also give me some satisfaction to see that my work has been also making some dent or some small progress in colorectal cancer world. Thank you.
So we can take some questions from the audience.
Lee, I wonder if, do you have any comments on what you see as the complexity that you'd recommend in a model, a predictive model to be used for either cancer screening or individual risk prediction. So in particular, I'm thinking, of course, of the push today to people in machine learning to have models that are very complex, use large numbers of variables. Statisticians and genetic epi people seem to still favor polygenic risk scores and moderate numbers of variables. What are the trade-offs?
Yeah, it's a very good question. We definitely get the pushback from clinicians a lot. They don't like that this is 1.2 million variants. It's just like too much for them, right? So I think the point is well taken. Even though we see the improvement using 1.2 million variants compared to, let's say, focusing on the known variants, significant improvement. But having this 1.2 million variants in the clinical care is still problematic, because it's not just like 1.2 million variants, it's a sum of 1.2 million variants. We have each of the weight associated with those 1.2 million variants. So what is the uncertainty of those weights? So there is definitely a desire to have a smaller number of variants that hopefully perform as good as this 1.2 million variants. So the way I see this is that I want to develop a polygenic risk score as best as possible, as predictive as possible. Then we start to work backwards and to see whether we can find or identify a set of, using the word parsimonious, a set of SNPs that predict as good as this 1.2 million variants. So I just want to know where the bar is, or what is how high that I can reach, and I go backwards. Yeah.
This is a topic which, of course, many of us are very interested in, but like from the previous speaker, you presented a very academic presentation, which is good. This is a university. But if we're going to make an implementation, I mean, I think the question is, can you actually implement this to do anybody any? In Canada, our biggest challenge is you can't get a family doctor. So you've got a test, which is a one-time test, which is nice. The target population is everybody. It's not like BRC1 or BRC2, where you can focus on people with a particular family history, because these PRSs don't really correlate with family. It's just, where you're going to do it, you do it on everybody. Someone's going to pay for it. Someone's got you go to the doctor. The doctors don't even take a family history. If I survey 100 family doctors and ask how many take a family history for colon cancer, the answer will be maybe 2 or 3. So, I mean, I've been following this literature for 20 years, and I just don't really think there's any practical possibility of implementing it on a public health scale, because who would be the target audience? How would you go about it? Who's going to pay for it? And how would you implement the findings? I think you should do a very specific, the UK Biobank, I guess, is publicly available. So you can go, I mean, there may be hundreds of variables within the UK Biobank that can be used to predict colon cancer, some as biomarkers and some as risk factors. I think I may even go have a look myself.
Mm-hmm.
But I don't, I'm just saying it's such a challenge in 2024 to use risk models in order to predict risk, but then to implement them and to reduce mortality from colon cancer, which I understand is going up in young women for some reason.
Yeah, that is, so my collaborator, Ricky, and I have been thinking about this problem a lot, like really a lot. We actually did talk a little bit about marker, but we didn't really make any effort, I must confess. So I'd love to learn more from you about this biomarker information. So we really have talked a lot, like what is our next step? Now we're doing all this work, and what's next? So we actually have been trying to get funding to do a pragmatic trial to incorporate the polygenic risk score into EHR, basically, in the Kaiser Permanente healthcare delivery. So the idea is that if a person is aware or more aware of his or her or their risk, they might more likely, hopefully, to take the screening. So that's sort of the premises that we work on. So we have not got funding on that, but I want to mention is that polygenic risk score, we can argue whether it should be, 1.2 million variants or it should be 10,000 variants. You really, as you mentioned, you only need to do it once and you have the information on the file. And family history, I know family history is notoriously bad, actually in EHR data. So once you have this polygenic risk score, it's sort of inherited risk for many phenotypes. So here I focus on colorectal cancer, but it can be for breast cancer, for prostate cancer, for any other diseases that one may consider. So a project that I'm only just like a small role is Emerge. I don't know whether you have heard of that particular project. So that project, they actually have done the pilot. They selected 10 conditions. Unfortunately, colorectal cancer was not chosen. They choose the colorectal cancer for familial syndrome, but not for the polygenic risk score. Because at that time, when we presented our polygenic risk score, our score performs not very well in African American population. The group feels that we cannot, even though it could perform worse than the white population, but they still wanted to be predictive in African American population. But since then, of course, we have made progress in our polygenic risk score in African American population. So anyway, so it was not chosen at that time, but they did choose 10 conditions, and actually sort of trying to understand how this polygenic risk score works in the clinical settings. They will return the results at the top 5 percentile to top for that particular condition back to the participants. And associated with that, returning the results, and there will be a set of recommendations, what they will do with the, with the elevated risk to manage their risk profile. So I think there's a lot of interest and there's certainly a lot of work to be done. And I do think, personally, I do think there is a differential risk between person to person, inherent risk between person to person. And we just need to harness the information better when we do the risk stratification.
Okay, just to follow up on that, a good news is my collaborator actually got a pragmatic trial for lung cancer funded, exactly to look at how do you bring PRS from bench side to bedside, and what will be the acceptability in primary care providers, and how does that motivate screening behavior and smoking cessation participations. So that's sort of the utility of PRS in that sense, beyond academic curiosities. So I have a question.
Yeah.
My question is about the recalibration. So I think adjusting for the difference in baseline hazard is a must when you go to a different population. What is more nuanced and hard to determine is what some of the covariates you will have different effects in different cohort as well. Let's say socioeconomic status in UK versus in US will have very different effect because of the healthcare system, right?
Yeah.
So in your sort of work, how would you recommend people recalibrate in those situations when you know that the covariates will have differential effect across population?
Yeah, that's earlier. Jerry and I was sort of discussing the similar question. Certainly from the EPI study, we actually see the relative risk as relatively robust across studies, but that does not preclude the situation where there is potential covariate effect. It's really hard to, that would be really difficult, right? So you have to work on some common ground to make that kind of transferring of the model from one population to another population possible. You have to have some common ground to make that possible. If we truly believe there's significant differential covariate effect, then maybe one should start develop their own risk prediction model. But another point that I sort of wanted to mention, it's a work ongoing, is that nowadays we have so many studies, right? So right now I'm just like meta-analyze it, treat them as like just 1 point estimate. But all those studies also provide us some understanding of the distribution of the covariate effect. And I don't think we have made good use of that information yet. And, with that kind of distribution of the effects, that might be something that, we can take advantage of.
I think there's one question in the chat from Paola. I would like to know your thoughts on how the imputation performance difference for underrepresented population will affect your methodology. For example, when you did 1.3 million variants.
Sorry, do you mind to repeat the question again? Didn't quite capture it. Yeah.
I think it's related to the imputation performance.
Imputation performance?
Yeah, if you are using underrepresented populations, how that will affect your results.
If I use, sorry, maybe I can look at the question. I didn't quite catch the question. Yeah. Imputation performance for underrepresented population. Yeah, good question. I have not looked at that particular issue specifically. Imputation has improved substantially in the last decade because the reference panel has been increasing diverse, and that's a good question. I have not looked at that issue specifically. Yeah.
Thank you. Any other questions? Okay. So before we finished, feel free to help yourself with the empanadas, and we can thank again Lee for a wonderful talk. Thank you.